Hey guys, welcome to Station 3 for this first day of talking about the atom. In this video, we're going to talk about average atomic mass. So average atomic mass is, at its core, a pretty simple concept. It is the weighted average mass of an element's isotopes. So a weighted average, while you might not have heard this exact term before, is a concept you're probably familiar with. If I were to tell you that the test grades from the last test in this class were 95, 99, 95, 87, 95, I'm making these numbers up, 82, 95, 100, 95, 86, 95, that works. So if I were to give you all of these test grades and ask you to find the class average, you would add them all together and divide by 11, and you would get about 93. So 93 is the closest to 95. Of all of the scores that we saw, our average is closest to this number that showed up 5 times. It's the same with your average atomic mass. We're going to take all of the different isotopes. And if you haven't been to Station 2 yet, then you don't really know what isotopes are, but it's okay. Someone's going to explain it to you. You're going to take all of the different isotopes, and you're going to take into account how often they show up. So here's the mass of isotope A. You multiply it by the amount of times it shows up, and that gives you a weighted average. This is going to make more sense when we actually go through it together. So it's a weighted average. Your atomic mass is a weighted average. It is the same number as that decimal number that is found on the periodic table. Okay, so you've got your square on the periodic table, you've got your symbol, you've got your atomic number up top, and then there's a decimal down here. This decimal number, that is the atomic mass. That's the average of all of the isotopes together. When you're doing these calculations, sometimes you don't even have to do math, depending on what you're being asked. You know it should be between the mass of the heaviest and the mass of the lightest isotopes, right? So our lowest grade, our lightest grade here was an 82, and our highest grade, our heaviest grade was a 100, and our average fell between those two. Your average is always going to be in the middle of your highest and lowest numbers. And it's also going to generally be closest, not necessarily always, but a vast majority of the time, it's going to be closest to the most abundant isotope. So our most abundant grade, our most common grade up here was 95, and our average was closest to 95. It fell the closest to that. So this equation right here of mass times percent abundance over 100 plus mass of a new isotope times percent abundance of that isotope over 100 and so on, you need to memorize this. This is not going to be given to you. But we're going to use it lots of times to practice, and by the time we're done practicing with it, it'll probably be in your brain anyway. It's important to note that the masses of a proton and a neutron are approximately 1. When you get together and talk with your Station 1 people, they are going to tell you that the mass of a proton is 1 AMU, and they are going to tell you that the mass of a neutron is 1 AMU. That's not strictly true. They're very, very close to 1, but this is rounded a little bit. And for the most part, this is fine. If you are not told a specific mass, this is fine. Use this. Call them 1, and it's good. But you should know that the actual mass number of each isotope is not a whole number. This blank is too big. It's going to be a decimal number. So if you are given a specific non-whole number mass, if you're given something like, I don't know, 12.01296 or something like that, use this number. If you are not given a specific mass number, then you will just come up with your own and do your protons plus your neutrons, or just use what is given to you in the name. And I understand that this is not making sense because we haven't seen any problems yet, but I just wanted to put this out there. So now that we've talked about it, we're going to see some problems where this comes up, and I will point it out again. So let's do some examples. Here we go. Example number 1, chlorine, good old chlorine from your table, Cl, has 2 stable, naturally occurring isotopes. These are chlorine 35 and chlorine 37. The relative abundance of each is 75.77% and 24.23%, respectively. And we're asked to find the average atomic mass of chlorine. So a couple of things about this problem. What our last slide was saying back here, this whole not a whole number, what that means is that this 35 is probably actually like 35.01296 or something like that. But for the purpose of this problem, since you're not given this decimal number, we can just assume it's straight up 35. We can just use that. But understand this is a rounded approximated value, so we're not going to take it into account with our sig figs. And here, where it says relative abundance, that means that if you are just walking down the street and you run into a chlorine isotope, there is a 75.77% chance it's going to be chlorine 35. And there's a 24.23% chance it's going to be chlorine 37. So chlorine 35 is about 3 times as abundant. It shows up about 3 times as often as your chlorine 37. So just thinking about this before we actually plug in and solve for our average atomic mass, we can say a couple of things. We know that our mass is going to be closer to 35 because our chlorine 35 is way more abundant, so we should be way closer to this one. We also know that it's going to be a little above 35 because the only other isotope that shows up is heavier. It's 37. So it should be a bit above 35. So we can use this to sort of check our answer, just make sure logically our answer makes sense. If we do this math and get like 90, probably we did something wrong. If we get like 35.2, that's going to be more in our ballpark. So we're going to go ahead and set this up now, and we're going to use that equation we learned a minute ago, which is that atomic mass is equal to, and we do the mass of each isotope times its percent abundance divided by 100. So our first isotope has a mass of 35 times that percent abundance that goes with it is 75.77. So we'll do 75.77, divided by 100. So that's for chlorine 35, this whole thing. And then we will add the only other isotope, which is a mass of 37 times that percent abundance is 24.23 divided by 100. And since we only have 2 isotopes, this is all we have to plug in here. So then putting this into your calculator, 35 times 75.77 divided by 100 plus 37 times 24.23 divided by 100 should give you an atomic mass of 35.48. And the units for atomic mass are AMU. This stands for atomic mass units because atoms are so small that we don't want to use grams because it would be a teeny tiny number of grams. So we use a special unit called AMU. So that's our answer. Let's double check, make sure it makes sense with what we said earlier. It's pretty close to 35 and it's just slightly above it. So looks like we probably did our math right. If you wanted to check on your periodic table, the value on your periodic table is 35.45. But again, there's a lot of rounding that went in here. We were using these numbers instead of whatever the full decimal value should be. So all things considered, we did pretty good. Great job. Let's look at another one. Number 2 says there are 3 naturally occurring isotopes of carbon. 3. There is carbon 12, there is carbon 13, and there is carbon 14. So 3 different carbons with 3 different masses. In a natural sample of carbon, which is most likely to be the most abundant isotope? We don't have to do any math here. We're not trying to find the actual average atomic mass. We're just saying which one is most abundant. So let's go look at our periodic table. And instead of putting that picture up here, I'm just going to draw in the tile we're looking at. So we're going to go look at our periodic table and find the square on the table that talks about carbon. Right, carbon has an atomic number of 6. It's got 6 protons. The average atomic mass is this decimal number underneath it, right? This number right here, that is the average atomic mass. So when we take all of our different isotopes of carbon and take their weighted average, we are going to get 12.01. And then underneath it, it says the name, which is obviously carbon. Oops. So our 3 options of isotopes are carbon 12, carbon 13, and carbon 14. Well, our weighted average is 12.01, which is really very, very close to 12. So we can say with a fair amount of confidence that carbon 12 is the most abundant because the average atomic mass, which is 12.01, is closest to 12. Let's look at one more. All right, number 3 here says the average atomic mass of boron is 10.81 atomic mass units, AMU. It has 2 stable naturally occurring isotopes. There is boron 10, has a natural abundance of 19.90, and the actual mass is 10.013 AMU. So in this case, instead of using the 10, we're going to use the 10.013 because we were given a more specific mass. So that's the one we're going to use. We need to find the mass of the other isotope. So we're still going to use our average atomic mass equation. We're just going to solve it out a little differently. We're going to do a little bit of algebra, and it's going to be okay. So first we will set up our equation. Average atomic mass is 10.81 AMU. That's going to be equal to, remember, the mass of each isotope times its abundance divided by 100. So we'll do the mass of our first isotope is 10.013. So I should write this out. Remember, your atomic mass is equal to mass of A times percent abundance of A over 100 plus the mass of B times the percent abundance of B over 100. This is the equation we're always going to use when we're solving for atomic mass. So we've got our average atomic mass is this 10.81. The mass of our first isotope is 10.013 times its percent abundance is 19.90. So 19.90 divided by 100 plus the mass of our second isotope, which we don't know. That's going to be our X value. So if you want to call that a question mark or an M, you can call it whatever you want to call it. I'm going to call it X because we're going to solve this like algebra. Algebra uses X's. Times the percent abundance, which we were not given. But all of your percentages should add up to 100, right? So if we know that our 2 isotopes together should add up to 100, then we can take away the 19.90 that belongs to boron 10. Subtracting that out, we get 80.10. So our mystery isotope must have a percent abundance of 80.10%. So we'll divide that by 100. Again, all of your percentages added together in your equation should add up to 100. So 19.90 plus 80.10, that gets you to 100. All right, so now we've got everything plugged in. We can go ahead and solve this out. We're going to do it in a couple of different steps here. Left-hand side we can leave alone for now, keep it as 10.81 AMU is equal to, multiplying this all together, 10.013 times 19.90 divided by 100 should give you 1.9926 plus x is just going to stay in x, but we can do 80.10 divided by 100 and we get 0.8010 times x. So our next step is going to be to subtract this 1.9926 from both sides. So we'll subtract 1.9926, subtract 1.9926, and on the left-hand side we will get 8.82 AMU is equal to 0.8010 times x. So we're almost there. Our very last step is to divide on both sides. Divide over there, divide over here. And we will end up with just x is equal to 11.0 AMU. So that's the mass of our mystery boron isotope. So if we were going to write that, we could write it as boron 11 as our second isotope. Okay, at this point, you have 3 more practice problems in your book. Go ahead and pause the video, work through your practice problems, work with your group, talk it over, compare work, help each other out. When you're pretty sure you've got the answers, go ahead and unpause the video and check. All right, hopefully this is what you ended up with. If this is not what y'all came up with, look it over again together, try and troubleshoot it. And if you really can't get there, the keys are posted on my website in more detail with it all worked out. So if you are watching this in class, that means it's almost time for you to rejoin your groups and teach this to each other, which means this is a really good time to make sure you've got this really solidified, that you're really comfortable with it, because in a second you're going to have to explain it to someone else. If you're watching this at home, obviously you don't have a group, but it does probably mean that you're done with day 1 notes. So great job, work on your quest, and happy studying.